Okay. Greetings. Hello, folks. Yeah. We'll get started once people take their seats. Greetings. Hello, everyone. Okay, hello everyone, welcome back. So there's a couple just little bits of news. So I sent out an email requesting that people watch some YouTube videos. So the YouTube videos are here. This one on Taylor series by 3 blue, 1 brown. So it's a little bit long, which is why we're not watching it in class. Could I get a show of hands for how many people watched it? Okay, most people watched it. Thank you for doing that. That's awesome. Today's lecture will go a lot better because of that. And then we've got this other one here where the graphics are way less high-tech. Could I get a show of hands for that one? Okay, no one watched that one. That's fine. Okay, so this is the multivariable stuff. Multivariate Taylor polynomials. So we're going to go over that today. Okay. Our mock test is tomorrow. Okay, so the mock term test is tomorrow at noon in IC 130. So please, please, please come on out to that. I'm trying out some software for doing the multiple choice questions. So that we've got, there's going to be some multiple choice questions on there. And I'm trying out the little app on my phone that scans them. So I just want to make sure all the software works before we do the real one and all your grades get lost. Yes. Someone emailed this question in. So if you can't make it, because I understand there is a class at that time, that's okay. It'll be posted on the blog tomorrow at like 2 p.m. Okay, so if you can't make it, the mock midterm will be posted at like 2 p.m. and you can do it at home. Okay, so you can do it at home, and that'll give you a sense of what's on the midterm. So if you've got that other class at that time, that's okay. But I recommend coming out tomorrow if you can. Oh, there's one other thing that I want to tell you about. It's not related to midterm information, but a contour plot came up in my real life, which is really cool. So I was like, we've been doing contour plots and we've been thinking about contour plots a lot. And last night, my dad called me up and said, I need some help with math. And I was like, what? Why do you need help with math? He drives trains, so. So it turns out that the lake that my parents live on is 11 inches lower than usual. So they wanted to know how much water is missing. So they sent me a contour plot of the lake. So this is the lake they live on. And we had to do some calculus to figure out how much water is missing. So this stuff actually happened in real life. And I was like, whoa, math is useful once. But yeah, so this is neat, right? So you can see that sort of the west coast of the lake is very steep and very sharply descending. And then the east coast of the lake is very slowly descending. So all these things about contour plots tell us about the structure of the lake. It's kind of neat. So we calculated it out, and there's 28 million cubic feet of water missing. So if you wanted to make like that amount of water, you would make a 300 by 300 by 300 foot box, right? So like much larger than this room. So there's a lot of water missing. Anyway, a contour plot happened in real life. Okay, so that's that. Mock midterm, good. And we're going to talk about this stuff with Taylor series, and we're going to talk about multivariable Taylor series. Okay, sweet. Okay. Can I get the thing to go up? Yeah, sweet. Okay, so one thing I forgot to ask about when we started Taylor series was this notation that we use. So a lot of the stuff in today's class is going to be phrased in terms of this notation sigma. So who has not seen this before? Has everyone seen this in one of their classes? Everyone seen it? Show of hands for yes. Okay, so I'll just briefly say what the parts of this notation mean, because we're going to be using it a fair bit. So this means right, so if we write the sum from k equals 0 to k equals n, this means right, the sum of k equals sum of f of k from k equals 0 to k equals n. So what does that look like? Right, we add up all the values of that function, putting in k at each time. Okay, so in programming terms, this is like a for loop. Okay, so we do for all k from 0 to n, add f of k. All right, so that's sort of the notation there. So I just wanted to do a brief reminder of how that works, because we're going to be using it in a pretty sophisticated way today. Okay, so I want to talk a fair bit about the Taylor polynomials in one variable, just so that we really have a feel for what's going on in one variable. And I want to follow the notation that the book uses a little bit closer than we did last lecture. Okay, so if we start at x0 and we add h, then we get the following approximation for our function. Okay, so we take a limit to infinity of the following thing. So we add up 1 over k factorial times x0 times h to the k. Okay, so this is our approximation to our function. What are the moving parts of this definition? This guy here is the kth derivative. And then this guy here is k factorial. So there's one thing that often trips people up with factorials. So I just want to spell it out now before we get too deep into things. We define 0 factorial in the following way. Okay, we define 0 factorial to be equal to 1. All right. The reason why we do this so that Okay, we do this so that the formulas work out nicely, and in particular we get n factorial over k factorial is n minus k factorial. Okay, we define it this way so that this kind of thing happens. Okay, so it's a choice, but it'll come up many, many times, and I just want to say 0 factorial is defined to be 1 so that things look nice. Okay. Okay, so now we'll talk about the, oh, yes, sure.
Are you sure that formula is correct? Because it doesn't seem correct.
Yeah, so what do? We've got, let's see, does it work? Let's take 3 factorial over 2 factorial. Oh yeah, that doesn't actually work. Right, yeah, sorry. What do I want there? I guess I want to multiply them. No, sorry. Sorry. Yeah, let's scratch that. Yeah, so what do we get here? Yeah. Or, sorry, not 1 factorial. Okay, so yes, sorry, this is off. Why do we define it that way then? I'll have to ponder that. Okay, so let's go on to nth order Taylor approximation. People in the back, can you see the blue chalk? Is that okay? Yeah, the blue chalk's legible? Okay, so the nth order Taylor polynomial of f of x at x0 is the following guy. It's the following approximation. So I write these little squiggly equal signs to mean that something is an approximation. Okay, so this is where we take the approximation up to order n. And there's a couple subtleties that we see now. One is, what's the 0th derivative of something? The 0th derivative okay, we're going to define this 0th derivative to be our original function. Okay, very good. Are there questions there? Right, so one thing I want to do is a little bit of a calculation of one of these nth order approximations, just in the case of an exponential function. Yes?
On the null here, should it be a hash 0?
Ah, yes, perfect. Yeah, this should be at h. No, this should be at x0 on both sides. Very good. Yeah, sorry, we want to say what this guy is here. Good. Nice. Okay, so let's find the third order Taylor polynomial for this guy at this point. So when doing these calculations, we find the first couple derivatives. Right, so we want third order, so we find the first three derivatives. Okay, so our 0th derivative, that's fine. Okay, we take one derivative. Two derivatives. Three derivatives. Okay, so we've got these guys here, and now we'll plug these into our formula. So we get the following approximation. Right, so we write out our approximation just up to third order, and then we plug in our values one by one. So we get 1 plus 2h Okay, so we get the following guy. Okay, and there's our third order approximation. Okay, so we replace our exponential function by a polynomial, which is easier to evaluate. Are there questions there or any typos there? Yes?
Can we put in the limit as well?
Ah, right. So we only want third order. So when we have some order, we go up to h to the n. So we only go to the power of h that it's asking for.
I mean, like, couldn't you just solve the limit? Because in the original formula, you have the limit as h or something.
Right. So we could get, yes. So we could give a limiting thing, but we want an order 3 polynomial. So let's answer your question, and we'll see how it looks different. Okay, so we'll give an infinite Taylor series now, and we get the following thing. Right, we get that we are approximately okay, so we get the following thing. We've got our derivatives are always 2 to the k, right? So our derivatives here are always going to give us a power of 2, right? 2, 4, 8, etc. So we put 2 to the k here, and then we divide by k factorial, right? Yes?
So why is it, when you're taking like an infinite limit, why is it just approximately?
Right. Yes, I guess I should say that this is actually an equality, right? So this is an equality right, so for nice functions, it's equal to its Taylor series. So here we can say that this is an equality. Okay. So here we're going to get an approximation because we take finitely many terms, and when we take infinitely many terms, we get equality. Okay, are there questions or thoughts there? Ideas there? Okay, so that's a little bit about the one variable Taylor series. All right, so now I want to go through some sort of long or extended examples to get us used to the kind of analysis that goes into these things. Okay, so we'll do a couple more concrete examples of Taylor series, and then we'll use them to prove the most beautiful theorem ever. So let's do a concrete example. Okay, so let's find the Taylor series for sine at 0. Actually, you know what? I want to do this over here. Right, so we want to find all of the derivatives of sine x. Okay. So So we start off with our original function. We take one derivative. Two derivatives gives us negative sine x. Three derivatives gives us negative cos x. And then 4 brings us back to start. Right, okay. We're going to need more derivatives to see the full pattern. Okay, so let's do the next couple. Okay, so we start over, right? Once we take 4 derivatives, we're back at sine. So now we start the cycle again. Okay, now that's enough of that. So we've seen the cycle. It repeats every 4 terms. Very good. Okay, so we've got all these derivatives. Now let's evaluate them at 0. Okay, very good. Let's do the first couple as well. Okay. So when you look at this list of numbers, there's some patterns that start emerging. So the first is that all of the even entries are 0. Right? We look at this thing and we note all the even numbers have 0 as their output. Yeah? So we want to focus our attention now on the odd entries. Right? These guys are where all the action is happening. Okay, and this is exactly the reason why sine is an odd function. Okay, all of its Taylor polynomial coefficients happen at the odd degrees. Okay, so Okay, so that's why sine's an odd function. But now we want to take the data we have and get a formula for the coefficients, right? We want a formula for these guys. So we're only going to look at the odd values. So we want a formula for the odd entries. Okay. So we're going to look at these guys and write them as odd terms. So we have 5 is 2 times 2 plus 1. 7 is 2 times 3 plus 1. Right, so here we've got k is 2. Here we've got k is 3. Okay, and we see that when k is even, we output 1, and when k is odd, we output -1. Okay, up here we've got, for f of 1, we've got k is 0, and here we've got k is 1. Okay, are there questions there? Any thoughts there? Yes, yeah. So there's another name for it, Maclaurin series. Right, so if you've got a Taylor series based at 0, that's named a Maclaurin series. Because if you don't call it that, if you call it a Taylor series, the ghost of Maclaurin will haunt you. Okay, so there's a slight name thing. I'm just calling everything a Taylor series. Because we don't need more names of dead British mathematicians. Okay, very good. So we're here. We want a formula for this guy. So we note that this value k matters a lot. So we get that this guy is -1 to the k. Okay, so that's a pretty subtle pattern to spot. But we can see that when k is even, we get 1. And when k is odd, we get -1. So we obtain that sine x is the limit Okay, it's the following guy. And I've run out of board space. So this guy, we've got a formula for him. So I get the following thing. -1 to the k. So there's our formula for sine. Okay, so what's really neat is when you use your calculator to compute a value of sine, it works with this formula here. Maybe it cuts it off at, n equals 5, but it works with this formula here. And this is the reason why mathematicians tend to prefer radians over degrees, is because the formula looks a lot nicer if you use radians. Right? So we choose radians so that we get a -1 to the k here. If we choose degrees, we get some weird number here instead. Okay, are there questions or thoughts about that formula? Yes? Right, so we used x here, so we can use h if you'd like. We can say right, and then that works with the formulas we had before. Okay, so there's what happens when we go to infinity there. Okay, so I'd like people to take maybe 5 minutes. And discuss the following thing. Try and come up with okay, so take 5 minutes and try and follow through this example, but using cos x instead. Okay, so try and find, using this idea, the Taylor series for cos x. Okay, and I'll come around and help out. So it looks like people calculated cos. That's awesome. The question came up a couple times. How does our formula take into account the even terms? Right? So for our formula for sine, right, we only have these h to the 2k plus 1s. We only have odd powers because sine is odd. For the even powers, we know that the coefficient is 0. So we've got 2k factorial h to the 2k. So this coefficient of 0 here means that we can just ignore the whole thing. Right? This all just goes to 0. Right? So we deal with the even terms in Taylor's formula by saying that they all go to 0, so that's fine. Okay, so now I want to prove, so now that you've done the calculation for cos, I want to prove for you probably the nicest formula in math. So let's leave that. So what did we get for cos? Okay, so what was the value for cos? What did we get as the Taylor series? Yes? Yeah? Awesome. Okay, so there's the cos Taylor series. Okay, and I want to. Oh, whoops! My mic's totally gone. Oops. I had a tail there for a second. Good. Cool. So we've got sine and cos. I just want to recall what's happening with E. Okay, so with E, we have the following fact. All of the derivatives are 1 at 0. So we get 1 over k factorial h to the k. Okay, so here are our 3 sort of complicated examples of Taylor series. Okay, and now I want to prove for you the most beautiful theorem. Okay, so this is going to be sort of the only time we use complex numbers, but it's the best place to use them. Okay, so this is the nicest formula probably in all of math. It's just so surprising, right? Like the exponential function, usually we think of it as becoming very large, going off to infinity, but these two functions are bounded, sine and cosine. So it's very odd, and this is probably the only place where we're going to use complex numbers. Okay, so that's the number that squares to -1. So I'd like to prove it using the Taylor series we have so far. So we take our formula for E, and we input I theta. Okay, and now we're going to break this sum up into the even terms and odd terms. Okay, so these are the even guys. Okay, very good. Now we've got 2 times k up here, so we're going to rewrite that. In the following way. So we split up the exponent. We put I squared to the k, right? That's I to the 2k, and then theta to the 2k. Okay, and now we do the same split on this side, but we've got this extra copy of I. We've got 1 copy of I and then 2k copies there. Okay. Okay. So now working with the I squareds. Right. Now, looking at these terms, we've got exactly the terms that we need for sine and cos. Right? We've got the even-powered terms with the -1, just like we need. So there's our sine theta. And here we've got the odd terms all multiplied by I. So there's our thing. So there's how we relate e to the I theta and sine and cos. Are there questions or thoughts? Yes, it is. Yep, sorry. Boop. Very good. That means you're paying attention. This is great. Okay. Very, very, very good. So this has the following kind of nice consequence, which goes like this. If we put in pi, then we get -1 plus I times 0. So we get e to the I pi plus 1. Okay, so this is the this was voted by the American Mathematical Society the most beautiful formula because it's got, you know, all these fundamental things in it. So I want to leave our discussion of single variable Taylor series at that. We'll take a 5-minute break, and then we'll pick up, or let's say we pick up at 10:15. Okay, and then we'll go into multivariable land. Good? You've got it? Okay, so now that we've gone through this big odyssey of single variable Taylor polynomials, we want to ask, how does it work for multiple variables? Okay? Okay, so I want to start off by doing a couple sort of warm-ups or like intro examples, and then go to a full generality. So right, so we want to approximate something in multiple variables. So what we're going to do is our first approximation is going to be the tangent plane. So right, we want to approximate base at x0. So our first approximation okay. So we get something that looks like this. X0 plus xy is going to have the following shape. Okay, so we take the partial derivatives of our function and put them against the two coordinates in our approximation. Okay, so this is our, we need, yes, sorry, that's fine. Good. So let's write down a tangent plane and see what that looks like. Okay, so we'll approximate this function at x0. Using our tangent plane. Okay, so let's see what we get. So initially we plug in 1, 1. Then we take our partial derivatives. Okay. And let's see what we get. Here we get 2, 2x, 2y. Okay, so our function is approximately this guy here. Okay, so as we move away, we grow like 2x and 2y here. Are there any questions about the calculation that went on there? Right, thoughts? Okay, so this is our okay, the first order Taylor approximation is this tangent plane to our function. Okay, and we've got this particular formula. Okay, now let's move on to second order approximations. Is the following thing. So I want to recall what this looks like for one variable. Okay, Sorry, just about our first order approximation, let's think back to what happens for one variable. Right, so for one variable, we had the following approximation. Right, so in one variable, our function looked like this, and we can start to see an analogy between the multivariable case and the single variable case. Right, so here. Sorry, before we go on to second order, we should say a bit about this. So in one variable, there's only one direction we can travel. Right, we can only travel in the direction of the real line. So we've got this plus h here. Right? And that plus h gets multiplied by a derivative. Right? So this is the thing that approximates our slope for us. And here we see the same kind of thing happening in two variables. Right? In two variables, we've got each of our different directions. Right? We've got the direction x and we've got the direction y. Okay, so those guys get multiplied by the derivative at x0, just like this guy got multiplied by the derivative at x0. Right, so these two terms are the value of our function, and these two terms are the contribution of the first derivatives. Okay, so that's sort of the analogy between one variable approximation and two variable approximation. Okay, are there questions there about the relationship? Thoughts? Okay, so let's say how second order approximations work. Okay, so for second order approximations, we do the same kind of thing. We plug in the value of our function plus all the first order terms, and now we add on the second order terms. Sorry. Okay, so for our second order approximation, we put all of the derivatives, all the second order derivatives together, and we multiply them by a half factorial. Okay, so this very much looks like our single variable analogy. right? So in a single variable, we only have 1 second derivative, right? And that term, this one term here, corresponds in multiple variables to this term here. Okay. Yes?
This is the x squared, xy, yx, y squared. Where does that come from?
Right. So these come from, we need the derivative of this thing, right? This approximation we're writing down. We need the derivative to agree with the derivative of our original function. Okay? So this whole thing is built so that the derivatives agree with the derivative of the original function. Yes. Good. Actually, wait. Sorry, one sec. Sorry. In order for it to agree, we need the following thing. Sorry, this bracket should only go over the two terms with squares. Sorry. These guys should be separate over here. Thank you for asking that question. It's a big point. Good. So this thing is built so we choose all the coefficients in order to make this happen. Okay, so let's do a second order Taylor approximation with two variables. Okay. Okay. Okay, so we'll find a second order Taylor approximation of this guy. At 0, 0. Okay, so we need to calculate several parts. Right, so we need right? We need this guy. We need our first derivative. Okay, so we need all the derivatives of first order, all the derivatives of second order. So let's get each of those values. right? Taking the derivative of this in x, right? We see that we've got e to the x times some constant. Taking the derivative in y, let me get that again. Okay, so very nice function, very nice derivatives. Okay, so all of these derivatives are given to us by taking derivatives of an exponential. So they all wind up agreeing. Okay, so let's plug this data into our second order approximation. Oh, and I guess I should say what these guys are at x0. So when we plug things into this, we get 1. And so for all of these values, we get 1. Okay. So now let's plug into the formula for our approximation. Okay, so inputting all the values that we have into this formula, all of the derivatives are 1, so we put 1s everywhere, and we get the following thing. Okay, so our approximation works something like this. Okay, any questions or thoughts there? Okay, so we get something that near 0 approximates our function well. Oh, sure. We've got a question somewhere. Yes.
Why don't we why is polynomial 2 factorial only multiplying f of xx and f of yy?
Right. Good question. Because when we take the derivative of this guy, we're going to get a coefficient of 2 coming out. So we want something that'll cancel that 2. But here, when we take the derivative, we're not going to get any 2's cropping up. So we'll get the value of the derivative there. Yeah. Good. Okay, so take a couple moments. and try and find the second order approximation of this guy. Okay, and then yeah, maybe take 3 or 4 minutes, try and find the second order approximation using this formula, and then we'll get into the general formula for these kinds of approximations. Awesome. So I want to take this up and then state in full generality how we do these things. So let's go over this second order approximation. So f of x good. Okay, so first off, we take all the derivatives of our function, right? So we've got them all here. Now we evaluate them. So we get 0, 0, 1, 0, and 1. Okay, so looking at this, we can see that Clairaut's theorem worked out. Yx and xy agree. Okay, so that's good. Now let's take the approximation. Okay, now we get the following thing. Okay, then we get this. So our approximation is 2xy. Okay, very good. So almost all of the terms go away, and we're left just looking at these two guys here, where we had some non-zero derivative. Are there questions or thoughts there? Okay, so very nice approximation to our function. Okay. So now I want to state in full generality the approximation theorem for many variables, many dimensions. Okay, in order to do that, we need a new piece of notation. Okay, and these are not used in our textbook. So this is sort of a special presentation of it. I recommend reading the textbook for an alternative presentation of this. But I think this is the nice way to state what's going on. So these are what are called multi-indices. Okay, so a multi-index is a list of numbers okay, this is the Greek letter alpha. Okay, so alpha looks like a fish. I don't know why that's relevant, but whatever. So we're going to use multi-indices to write down the full statement. Okay, so the first thing we need is the following guy. If we write one of these multi-indices with a factorial, we mean the following thing. Okay, we take each of the entries and we take its factorial. Okay, so whenever we use one of these indices, all of these will be whole numbers. So we can take factorials of them. Okay, our other piece of notation is where we put bars, and that means we add up the entries. Okay, so as an example of what's going on there, two, 3 bar, that's going to be 2 plus 3, which is, I think it's 5. Okay. And 2, 3 factorial will be 2 factorial, 3 factorial, which is 12. Okay, so those are 2 ways in which we use multi-indices. Okay, and then the last way in which we use them is like this. F sub alpha okay, very big piece of notation, but we have alpha 1 copies here, alpha 2 copies here, and alpha n copies here. Okay, so sort of sophisticated piece of notation, but not terrible. So if we had f sub 2, 3 of xy, that would be the following derivative. Be a 5th derivative. Okay, so that's a lot of notation all at once. There's lots of things going on there, but it allows for the nicest statement of Taylor's theorem. Okay, so the nice statement of Taylor's theorem in multiple variables is as follows. Oh, dang, we need one more multi-index thing. Okay, we need one last multi-index thing, which is this. Okay. Okay, very good. So if we have a vector to an index, we get something like this. Okay, so those are our simple examples. Okay, so lots of notation to digest all at once. But let's write down Taylor's theorem in these words. Okay, so it's approximately the limit k goes to 0 of n. Now we have to add up over all of these derivatives. There's lots and lots and lots of derivatives. So what do we get? We get sorry, to put things in the same notation as the one variable case, we've got x0 plus h. And then we get this. Okay, so this is the sum over all possible derivatives. Okay, so now we see why we need these different factorials for different terms, right? Different terms will have different multi-indices. Okay, so if we have something like this, right? In our second order Taylor approximation, we had 2, 0 factorial, which is 2. Just one. Okay. Very good. So this is our statement in full generality of Taylor's theorem. So this works in any dimension. Okay, very good. So we're going to explore this a fair bit more next week. We've got a week to kind of summarize and do all the things in the course. So this is a lot to take in right now, but we've got a week to go through it. Okay, so that's where I want to end off. If you've been taking PDF notes, those are very valuable. Okay, so if you have PDF notes, please send them to me. And we'll talk about Taylor's theorem more next week.